new things for redox this year is that you have to actually justify whether a reaction is going to occur or not. And the one I want to use as my context for this is what happens when we put copper in nitric acid. I'm not going to do it in front of you because it makes a poisonous gas, so I'm sorry, just not going to happen. So if I put copper and nitric acid together, so copper is a pinkish metal, nitric acid is a colourless solution. If this is concentrated enough, you get a fast enough rate of reaction to observe something happening. You get fizzing, which is what you expect for any metal going in an acid. And you get a blue solution, so the copper is turning into copper ions. So we get this blue solution, and we get fizzing, but actually what we notice is that it's a brown gas, not a colourless gas. So the blue solution is pretty obvious to know what's happening there. We've got, sorry, use a bit of a colour coding. We've got copper turning into copper ions, and this is an oxidation reaction. So the copper is our reductant. So it's going from an oxidation state of 0 to +2. It's losing 2 electrons. So we know that it's being oxidised. Okay, so it's an oxidation reaction. However, nitric acid is made up of 2 different parts or ions. One is H+. Well, that's feasible. That could happen because this is a gas. This is a reduction reaction, so it could happen. Or the fact that it's a brown gas tells us that it's more likely that the nitrate ions are actually reacting. I'm sorry, I could go through how to balance it. I'm just going to put it up here quickly for you. Okay, so just double check that. 0. Yep, cool. So the brown gas is nitrogen dioxide. So actually this is the reaction that's occurring. So I'd actually ignore this top one here and I'd put these two together to give my net equation. So Cu plus 2 nitrates plus 4 hydrogen ions goes to copper 2 plus 2 nitrogen dioxides plus water. Okay? Sorry, I saw a hand up there, so I'm going to go to
that. Since H2 is colourless, how do you know that it is not made and that
cool.
it's not used?
So maybe both reactions are actually occurring. This is a bit more complicated than that. Okay? And this is where electrode potentials or reduction potentials come into it. Potential means how likely is something to happen. Okay? Everyday language. What's the potential of something happening? We often talk about your potential in your reports or when we're having a chat about how well you did in a test. So it's how easily or how well can something be reduced. That's why it's sometimes called reduction potential. What we find is that we'll answer that question using some maths and using these electrode potentials. Every pair has got a reduction potential. So we've got 3 pairs in here. Copper, hydrogen, and nitrogen dioxide. Okay, and they're pairs. And we can look up their electrode potentials in a book. And we find that, sorry, bear with me here, the copper 2 plus copper electrode potential is 0.34 volts. Okay, I'm not going to go through how we calculate or how we find these out yet. Just trust me on these. And these values will be given to you in any assessment. All right. Sorry, I shouldn't have to look this one up. The hydrogen one is what we call the standard cell or standard half cell. So it's 0. Everything else is measured against hydrogen. Okay. Then we get the last one we've got here is the nitrogen dioxide one, and I'm hoping like heck I've got that handy, which I don't, of course. Murphy's Law. Not what I've got on there. So we'll look that one up in a moment. So I'll get that one later on. Okay? And what we can do is we can use this data to calculate if a reaction is spontaneous or not. In other words, does it happen? So to answer that question, how do we know this one isn't happening as well, I'm going to use the data I've got for these two to show you. I don't actually need this one because I know this one happens because I saw the bubbles that were brown and I know that happens. So what we find is the electrode potential for, we call it a cell, but for a reaction, is equal to the electrode potential of whatever's being reduced, so because it is reduction, minus the value for whatever's being oxidized. So redox, it's read as redox. Remember, that's what we call a topic. So the reason this is net as minus is actually it's the sum of all the reduction potentials, but one of the things is being oxidized, so it's being reversed. So remember when we were doing energy reactions, if you reversed a reaction, you reverse the sign of its enthalpy change. This is really the same idea, okay? Because we write these all down as reduction reactions, if I have to flip one of them to make it oxidation, then it has to change from, in this case, positive 0.34 to negative 0.34. So this equation helps us remember that. So here's what it will look like. If I'm looking at the hydrogen one, because that was the question that you guys just were asking, how do I know this isn't happening as well? Then the E naught here is going to be the reduction reaction. Electrons are on the left-hand side, so it's reduction, they're being gained, is 0. Then I need to subtract the oxidation value, which is 0.34, because it was with copper. And that equals negative 0.34 volts. Because this value is negative, for the reaction, okay, it's called cell, but it's also reaction. Because it's negative, we say it's not spontaneous. And remember when we did energy, this is like Gibbs free energy being positive. Okay, not spontaneous. It means it won't happen unless you drive it to. Because the unit is volts here, guess how you could drive this reaction to occur? Spot on. You'd pump electricity into it. So to make something not spontaneous happen, you'd actually have to plug it into a power source to make it occur. Okay? So this reaction could not occur without a power source that overcame that 0.34 volts. Sorry, I don't have a value for the NO2, but it would tell us that the NO2 value must be higher than 0.34. Must be higher than 0.34. Because this number here, minus 0.34, has to be greater than 0. Okay? So electrode potentials are values you'll find given to you in a data table. They were found out by measuring them against hydrogen, actually. Okay, where hydrogen was being oxidized and the other thing was being reduced, to see what we got as the value. Then, once you've got that data, you can see which chemicals you're mixing together, and you can look at which one's being oxidized, which one's being reduced, plug it into this equation, and if your value is positive, the reaction does occur. It's what we call spontaneous. If the value is negative, then it's not spontaneous. That reaction will not occur. All right, give you one more quick example. Because I'm sorry I don't have the one there for the nitrogen dioxide. If I was putting copper into a solution of, let's say, iron, no, bad example because we can have two oxidation states, into a solution of magnesium sulfate, okay? Then we can see if that would react or not. Now we know our activity series. What would we predict if you put copper into magnesium sulfate? What would you predict would happen, if anything? Which one's more reactive, if we were talking about an activity series? Magnesium. So we'd expect that to be staying as ions, wouldn't we? Yep. So if we put copper into magnesium sulfate, then we're needing magnesium sulfate to be reduced and copper to be oxidized for a reaction to occur. So let's have a look at what would happen with that one. So the E value for this reaction would be, we'd need the magnesium to be reduced, so negative 2.36 minus, we're putting copper into it, this one here. So we're going to end up with negative 2. Quickly doing maths, 70, isn't it? Okay, so it definitely won't occur. However, if I was to put magnesium into copper sulfate, then the reduction would be the copper 2 turning into copper, wouldn't it? Okay, so that would be 0.34. And I'd be subtracting, so magnesium being oxidized, so I'd be subtracting negative 2.36. So this reaction would be spontaneous. And we've all done that last year or the year before, where you put magnesium into copper sulfate and you see that copper forms on it. Here's the mathematical proof that it does indeed happen, it is spontaneous. And we're looking at electrochemistry anyway. Any questions on that?